second session, and I'd like to invite Professor Subhabrata Majumdar of the TIFR to introduce Professor Richard Bond.
It is my great pleasure and indeed an honor to introduce Professor John Richard Bond, or Dick Bond as we all know him. Professor Bond is the university professor at the University of Toronto and currently the director of the Canadian Institute of Advanced Research in Cosmology and Gravity, and formerly he was the director of the Canadian Institute of Theoretical Astrophysics. Now, Dick has been a pioneer, a leader in many areas of cosmology, and of course, you know him most for his, I would personally say, his work and the impact on the physics of the cosmic microwave background, which Jim in his previous talk did show you, like these pictures. But apart from doing really pioneering work in this thing, so this large subject of cosmology, the thing that amuses me is that he comes up with all these buzzwords which really sticks into the people who works on these fields. For example, words like gastrophysics, very akin to gastronomy, but over here to describe gas physics in cosmology. The cosmic web, the first distinction of cold dark matter and hot dark matter. Words that we use all the time. For example, cold dark matter will be one of the key areas which LHC is going to look at. But to me and to many, the biggest accomplishment of Dick has been not only to take this field into the next level, but to take a fledgling institute, Canadian Institute of Theoretical Astrophysics, 25 years back, when no one knew about it, and to take it to a position, a world recognition, which is truly enviable. It has nurtured a large number of postdocs that just spread all over the world. So, in some sense, he has made a tree which has sort of spanned the whole world. He has been highly awarded for all his work, and I'm not going to go to the list of awards, but let me just say that it is very rare for a country's highest civilian award to be given to a scientist. Scientists do get awards which are made for scientists. But to get the country's second highest civilian award, that is very rare. So Dick was conferred the Order of Canada. To give it interpret in Indian terms, it will be akin to Padma Vibhushan because the second highest award. And this basically says where it stands in the community. So without any other delay, let me ask Dick.
Well, thank you, Shiva. I hope that you have been well here. No. Now you can hear me. Okay, I hope that you were hopefully quite mystified by my title. Cosmic Information Theory and Analysis was, of course, a play on the words of CITA, the Canadian Institute for Theoretical Astrophysics, which is my home institute, and which many in this audience actually have been through its hallowed halls and have gone off to rule India, at least scientifically. And so this is a great aspect of our institute. But from bits in it, and one of the great coiners of all time was Johnny Wheeler. Johnny Wheeler was the graduate supervisor of one Kip Thorne walking down the aisle right now. But before I get to him, I am going to invoke the presence of Boltzmann. On Boltzmann's tombstone, there is an equation, S equals K log W. In our terms, it is entropy equals some constant, curiously called the Boltzmann constant, logarithm of the number of possibilities. And the universe offers to us a lot of possibilities. And it has only been relatively recently that we've been thinking about it in those terms. And I am caught by this information revolution in terms of our thinking. That probably means I'm becoming a Wheelerian. Let us remind ourselves that one way or another, and we had this discussion the other night, black hole owes its origins as a terminology to one Johnny Wheeler. Now I am in Wheeler split his existence into 3 units of physics. In the 30s, 40s, etc., it was particles. And then he went on to fields, which actually took him into gravity, which he did so much for. And then, towards the later years of his life, he said, now I am in the grip of a new vision, that everything is information. The more I have pondered the mystery of the quantum and our strange ability to comprehend this world in which we live, the more I see possible fundamental roles for logic and information as the bedrock of physical theory. And what I like the best, I continue to search. And he did that, of course, right until his dying day. And there are many ways that I could play out this game. What do we mean by reality except the results of observations? If you haven't experienced it, does it indeed exist? Trees in the wood and all that stuff. Then some graduate student of Wheeler's was asked and said, the observer confers reality on the past by observing it, and offered the Big Bang as an example. So today we are going to observe the Big Bang. But another revolution which has been occurring is been growing and growing in excitement level, and that is the Shannonization of the universe. Shannon, 1948, identified entropy, which Boltzmann had shown heat was related to in terms of number of states. He related the content of information to entropy. So we all understand entropy at some level as some level of randomness, etc. But he identified this with information content. And so this has been embraced by anybody who deals with computers. And as we know, computers have taken over the world. And so this is a big new revolution. And now we add the word quantum to it, and that is called quantum information theory. And the universe is just an example of an entity in quantum information theory, or at least so my quantum information friends would like me to believe. But dealing with the content of information is very different from dealing with the quality of information. And so quality is going to be one of the themes of today. Now, I will invoke one other great physicist. Actually, he wasn't a physicist at all. And those of you who remember Laugh-In from the 60s, an old television program in North America, Marshall McLuhan. The medium is the message. Of course, that's a very curious phrase. What does it actually mean? So I can make it mean what I want it to mean. And it may be that the medium, all around us, is just the message. The messages, the message. Okay, so enough philosophy. Oh, wait a minute. I will give you more philosophy. Okay, so as I try to introduce many of the concepts, as we take a sweep through the universe from its ultra-early beginnings to now, I want you to bear in mind that the universe is system, mainly me, or you, and reservoir, which is everything else. And they are all entangled together. So there is maybe one unique universe, maybe it's multiverse. How do you do the counting? Don't know. That's an issue that we aren't going to address today. What I'm going to say, though, is that you have no choice but to say here, there, that, experiment, observe. System, residual. Anybody who's done any thermodynamics, any statistical mechanics is very used to these ideas. You can think system is signal. Signal is what we want. Signal's good. Residual is noise. But what's one person's noise may be the absolute signal of relevance to another individual. You can also think of the residual, that which you don't really care about, is hidden. So a nice way to think about this is, I was in Buenos Aires in the summer, and this couple is doing the tango. And one of them, let's say, is a reservoir, and another one is a system. And you may not have ever seen somebody do a tango, but the legs move with nearly the speed of light, if not beyond the speed of light, the speed of neutrinos. So these legs, they totally intertwine with each other at incredible speed, but they never collide. And that is entanglement, or entanglement, as I like to say. And that is the dance of the universe. That is to say that all things are interpenetrating each other in some very complicated way, where all of the phases are mixing. Since I'm in India, I tried to get from my good friend Shubha here a way that I could project this into an Indian context. And so this is someone who I've now learned is not just Shiva doing the cosmic dance, but the name is Nataraja, or it originates from there. And I didn't want it to be the dance of destruction, which of course is what we associate with Shiva annihilating the universe. But there is another gentler version of the dance in which the things are all weaved together to produce some great harmonious thing, but with complexity coming out in this cosmic dance. Complexity is surely what we have around us, and as Jim pointed out, this began, at least in the region of the universe we can see, as a very simple thing. Now we can actually put an accounting of how much complexity we have at some level, which is the total entropy, the information content, a la Shannon. And it turns out that that number within the region of the universe that we can see is approximately 10 to the 90th. There's a number to wrap your mind around. 10 to the 90th. Non-trivial number, but bits that make up the knowledge in our universe, but most of them are just thermal. And actually, that entire content of information is more or less encoded in two numbers. One is the temperature of the microwave background today, which is just a few degrees above absolute Kelvin, as Jim talked about. And the other one is the inverse of the Hubble expansion rate, which is a good measure of the age of the universe, of cosmic time. You have to be a little more precise, but about 14 gigayears. Those two numbers, with the photon entropy and some neutrinos thrown in for good measure, give us this number. There is another number which is even more mysterious, and I would challenge Kip, the great gravitational theorist, to give us a cogent explanation of what has come to be called Gibbons-Hawking entropy, that once the universe becomes, and we will get to this at the end, which is the fate of the universe, once lambda dominates, if it does dominate, what will happen? There will be this curious thing, it's called the Gibbons-Hawking entropy, that will be left over, and it will be 10 to the 120th. Another arbitrarily large, very hard number to understand. The amount of complexity in this room, in the atmosphere, if we take one proton, neutron, or something, it's a bit per baryon. That includes all of the little jiggling around. That includes all of the rotation around of the molecules, all of their vibrations, etc. Look at the difference in numerology we're dealing with. As we go to hotter environments in the universe, like the centers of clusters of galaxies, the number builds up, but it's nowhere close to the amount of information, entropy, information content that's in photons and neutrinos. Now there's another line to this whole discussion, which is that we are observing the universe. And so what we do is we send out our spacecraft or use our telescopes to gather in the bits of information that we can capture from this huge number, 10 to the 90th. So the great WMAP, the satellite experiment, I'm not even sure that Ichiro Komatsu, who's in the audience, knows this number. But there are 10 to the 12 bits that were sent down from this satellite over 9 years, and that has delivered to us the unveiling of cosmic mystery, the numbers that we have got. Planck has more bits, and the Atacama Cosmology Telescope, which may or may not have been in one of Jim's pictures, even more. This is a result of increased and improved technology. And what we do is we take this arbitrarily large number of bits, most of which is just, thermal bits in detectors, etc. And we compress it. We compress it onto the highest quality bits we can imagine. For example, the bits that describe how much stuff there is in the universe. Ordinary matter, dark matter, cosmological constant stuff, what the nature of those fluctuations in the ultra-early universe that grew to become all of us. We compress that onto about 7 parameters, and these 2. That is to say, there is this remarkable simplicity, apparently, to the message that we're getting from the cosmos, which is that things can be described in a simple way. Now, let me say that I don't think that's going to be true, and you better hope it's not true, because we want to have more parameters for you to measure as time goes on. We want more parameters. So I'm going to show you the famous Ouroboros, but in my own way. So apologies to the sophisticates in the audience, but you will not believe how much information there is in this snake, which is swallowing its tail. And we're going to go at various levels through this thing, and we're going to work our way backwards, forwards, and around to look at all of the different time, the evolution of time in the universe, the expansion of the universe. And here we have the cognizant being, which I am going to take as my standard figure, Pythagoras, whose name I hope that you recognize, looking back and trying to learn all about the different sections of the universe. And surely enough, we can do that, and that's the most amazing thing of all. I'm going to come back to this so often you'll get completely sick of the figure, so don't worry if you haven't figured out everything in that figure yet. So Jim very nicely took us a walk through history, and so I'm going to give a highly compressed thing. Filtered, compressed, reduced. That's what you have to do with information. So I am beginning with Pythagoras. Why am I beginning with Pythagoras? Because he told us something that was absolutely dramatically amazing that we should think. We should think that the cosmos, and he, I think, introduced the term, the cosmos can be described by mathematics. What an outrageous thought that is. That, of course, underlies every single thing we do in terms of the physics. As well, he was dealing with wires or some such thing, with strings, and introduced harmonic analysis, frequencies, wavelengths. And the other thing that I just found out from a Pythagorean expert at the University of Toronto is that he and his group were heavily into counting. And so, in a sense, he was the first digitizer. So, we're all just Pythagoreans. And in fact, many of the greatest scientists that have ever been have called themselves Pythagoreans, and I hope that all of you in the audience will consider yourselves Pythagorean. This is Democritus Adams. This is Roger Bacon, who said, you must take theory and make a marriage with experiment. And of course, that's been the history of our time. But you might note that the various people, who you may recognize or not, as we move forward into modern times, hey, somebody's missing. Maybe you'll come up. Galileo, Newton. So I was in Edinburgh, and I was given access to this secret room. And in the secret room, there is the death mask of Isaac Newton. And of course, just like in the movie The Mask, I was going to put the Newton mask on my face and hope to channel the being himself. It didn't work, unfortunately, but there I am with Newton's mask. That's Immanuel Kant. That's his idea. Dalton, Rutherford, man of the last century, Albert. Friedman, we saw. Lemaitre, Jim is probably the purest Lemaitrean I know, so lambda was no surprise to him. De Sitter, the great George Gamow, 1, 2, 3, infinity, and equally great Fred Hoyle. Steady state, Big Bang. He coined Big Bang to make fun of him. Steady state, Big Bang. You know who was right? He was right, but in a complex way. Let's see if the next guy's going to actually come up. Yeah, Sakharov. Remember Sakharov, the great dissident? He was the one, at least as far as I know, but it now sounds like I better go back to my books because maybe Lemaitre did it, who declared that we could consider lambda on the other side of Einstein's equations and say that it's a measure of the energy of the vacuum, the energy density of the vacuum. And that is just mind-boggling. So you better know that it's there. So you use various things. The size of the universe, measured by something called A, the rate of expansion, something called H, we'll see that these materialize again, and then something which is measuring the acceleration of the universe, which we'll also see at the very end. Okay, now we're back to here. We've seen our Pythagoras, he's looking back, as are we. And so I'm going to just have a little brief aside on when protons and neutrons formed and just after it. So there is a quark soup of some sort that we will hear a lot about, presumably from John. Protons and neutrons form. This is very early in the history of the universe, so let there be protons, neutrons, alpha particles, and then there are the usual kinds of photons, neutrinos, and electrons. There used to be a lot of positrons, but they would have all decayed by E plus E minus into photons, antimatter decaying away. So this is an iconic figure showing the periodic table of the isotopes. You probably have all seen the periodic table of the elements. This has all sorts of different numbers and things associated with it because each nucleus may have many different states. And so the remarkable thing is we understand this very well. The remarkable thing is that we understand its cosmological origins very well. Pretty well, anyway, throughout this whole range. And the big lesson, so most of the elements up here came from exploding stars. This is my thesis advisor chatting with this costume lady in Sweden once upon a time. Willie Fowler got the Nobel Prize for this work. You know, the various constituencies. And so with the microwave background and large-scale structure and other things, this is the number, not here in this room, the number of baryons, that is to say protons and neutrons, out in far, far outer space, which is something like 1 every cubic meter. Wow. That is to say, you go a meter and you find a baryon, you go a meter and you find another one. It's amazingly not very dense. But that is not the story. The story is, here's a lot of data, and here is an amazing thing. This is what we inferred from the theory of Big Bang nucleosynthesis, and I might say that Jim Peebles played a very big role in this as well. And here is a number to look at, and I won't even bother telling you what the axes are, that isn't the issue. And this is what you got with the microwave background and large-scale structure. The numbers agree, spot on. What a story that is. So that from completely different methods, we have learned how much ordinary stuff there is in the universe. And so there's a stuff of various sorts in the universe, of course. Essentially, by definition, it must all sum to 1. That's a mystery which I'm not going to tell you about. This is in funny units. But we have radiation. We have neutrinos. We have chemical elements, other than hydrogen and helium, heavier ones. This is much of the stuff that makes us up. We have stars. We have hydrogen and helium. We have dark matter. We have dark energy, as we have just heard, both of these mysteries. We have gravity waves. We've heard about that. And we have black holes. And here's an inventory, as of now, of the amount of stuff we have. Radiation at this point, 0.005%. The neutrinos with a higher percentage, and yet coming from basically the same origin, and that's because neutrinos have mass. And so they're contributing some kind of mass, and this is uncertain. But what is so curious is that our best bets for the neutrino masses means that the mass in these cosmic neutrinos just happens to be about the mass of the stars of the universe. What a weird thought that is. Who ordered that? The free hydrogen in helium is much bigger. It's about 4%. The dark matter is about 22%. The dark energy is about 74%. And you might marvel at this remarkable degree of precision that we are claiming that we have determined these numbers. This one, you see that it's not quite necessarily as certain as that because it might not be cosmological constant for the dark energy. And the gravity waves sum to quite small numbers, but we can detect them. And the black holes in the centers of galaxies sum to some 10 to the minus 7 on these scales, a non-trivial number. Okay, so now I'm going to take you into the realm of some experiments to show you how we get some of the data. And so we're going to go to the regime of the first light. So we've been here, and now we're going forward. Before this, the universe was opaque, and then at about this period, 400,000 years after the Big Bang, when it was compressed by a factor of about 1,100, it turns out that the ionized medium turns into almost completely neutral medium, frees up the photons who propagate to us, but because the universe is expanding, the wavelengths stretch out, and it comes to us from something that's basically red to infrared here, that when we detect it up here, it's this very low temperature microwave radiation. So, an aside on the gathers of cosmic information. Since I'm a theorist, I'm going to flash on a few theorists. Here's an individual that you might recognize in the audience, Jim Peebles, that's the famous Neldovich, Sunyaev, Martin Rees, already at a young age iconified as a statue. And this was from a very raucous party around 1980 in Berkeley. That's Joe Silk, that's Georgia Stapio, and that's me looking on as we had our fun discussions about the microwave background back then. Okay, we've been through this, the Nobel Prize in Physics, and I'm very pleased that Canada was highlighted by Jim by the equivalent thing. Kobe got the fluctuations on large scales of the microwave background, and this is the sort of resolution that it had, and this is the resolution of the WMAP satellite that was launched in 2001. It was a picture I actually took. Jim was there as well. It was on a Delta rocket, and off it went off into space, looking like this, spinning around. Ended its mission in 2010, and sometime in the next year, it's going to give its final numbers, WMAP 9, so-called. So this is a picture of a baby seen at Kobe resolution, and this is the same picture of the baby seen at WMAP resolution. And you can't read it, but you can actually read the label on her thing that's around her wrist. And at Planck resolution, you would see even more. Another thing we've done with the microwave background is we focused in, going deeper on smaller regions. This was a very famous experiment called Boomerang. And this is a very nice experiment. It's the 2011 variety. Jim showed some results from the South Pole telescope, in spite of the fact that his next door neighbor is Lyman Page, and he should have been extolling the virtue of the Atacama Cosmology Telescope, of which Lyman Page is the principal investigator. This is a combination of WMAP and the Atacama Cosmology Telescope, and what it does, it extends the range of WMAP enormously in a way which I will show you. But first of all, I want to go back in time and say that even with the early Boomerang flight, which was actually a balloon flight going to the top of the atmosphere, going some, actually it went all the way around, it's called Boomerang, it went all the way around Antarctica. Here is reality. And here is a simulation simulated the same way. Now, you won't see the spots in actually the same location because a random number was thrown with this theory. But just visually, you got to say, hey, wow, they really look quite a bit alike. We do this with much more precision, but I think the visual certainly shows you that we're on the right track in order to understand what's going on. I'm involved in a very large collaboration. Mainly, it's European Space Agency. NASA's involved, Canadian Space Agency is involved. It's called Planck. And here, you're going to see a movie taken out at L2. No, the movie is just a simulation. What happened is the spacecraft launched from French Guiana in 2009. It's been taking data ever since. This is going to show you the kind of pattern on the sky that it looks at with its bank of detectors, and it sort of it gets the information in from these regions of the sky, and it goes around and around and around, and as it does it, it paves the sky, and so you end up getting what's called one sky survey. Planck is in its 5th sky survey. The mission nominally was 2 sky surveys, so it is wildly successful. The quality of data is excellent. And it leads to a picture, something like this, football, showing that the universe is really a football. No, up here is the North Pole of the galaxy, the South Pole of the galaxy. This is joined to that. This is the plane of our galaxy, and I will say a few more words about this funny color combination. The big thing that makes it such a remarkable instrument is the degree of cooling, and how much could have gone wrong, because you don't get to, hop in your airplane and go zooming out to L2, which is 1.5 million kilometers away. So everything had to work perfectly, and that it did is a triumph for the experimentalists involved. Another thing that we're heavily engaged in, here is Chile, here is Bolivia, here is Argentina, right at the corner at the driest desert in the world, 5,200 meters up. There I am, actually there, intrepid experimentalist me. It was actually very cold, but I was showing my intrepid Canadian character by stripping down and saying, not cold for me. Anyway, this obviously isn't the telescope, this is a shield. The light comes in, there's a telescope here. It goes into ultra-sensitive detectors, a factor of 50 more than the sensitive detectors on Planck, which means that it's such a fabulous instrument. And it's not the only one. There are lots and lots of experiments. What we're looking for when we're trying to peer into the ultra-early universe is we're trying to look at this little motley pattern here, which this is this Atacama Cosmology Telescope in WMAP looking like this. By the way, Emir Hajian, who has the office next door to me at CITA, did his PhD degree at IUCA under Tarun Suradeep, who's sitting there, big Indian connection at CITA. And this is that, except this is even higher resolution, but it's only a tiny little bit of this whole map, so this is all sky. These are things like what's in our galaxy, and there are also a lot of points of what's outside of our galaxy, but emitting objects like radio galaxies or infrared galaxies or stuff like that. We have to understand all of those things if we're going to get to that precious thing with very high precision that sits behind it. So, in fact, if you actually count up the number of veils that hide it from us, there are actually 7 veils. Now, you may know of Salope and the 7 veils. And so we are stripping off these 7 veils to see the ultra-early universe. Okay, Jim showed a figure of WMAP plus SPT when you do what is in effect a harmonic analysis, a Pythagorean analysis on that picture. And we do very well indeed, too. Okay, there is lots of action in this subject. So here is a timeline. And WMAP was launched back here, COBE back here, and experiments happening more and more and more. and the amount of data volume is becoming unbelievable, and it's all precious information trying to unveil the secrets of the early universe. But there's another thing that you have to do. You have to process that information to get these few precious bits. This is a very big computer in Toronto, and so I'm going to read this because you can't read it. I'm not even sure I can. Simulate universes from ultra-early beginnings to the ultimate end, turning a few parameter theories into petabits of information. That's the simulation side of theory. Then there's the processed data side, where we take compressed petabits. Peta is 10 to the 15th in this game, lots of bits. Raw observed microwave background and various large-scale structure information of the sort that Jim showed, and we process it into very high-quality bits, namely those 6 parameter theories. And so there's a lot of crosstalk, all being done by very large computers. And Tarun just told me India is making high-performance computing a huge priority here, so it is a path where you can make a very big step. Okay, now we're back to our Ouroboros, and I'm going to show you how you can use such simulations to understand all of the stuff that Jim showed us, through galaxy formation all the way through to cluster formation and the formation of a very beautiful cosmic web. Okay, here is an interesting simulation because it emphasizes the hubris of physicists. Because we think that this is probably, roughly speaking, the way things look in the first 10 to the minus 40 seconds after the Big Bang or so. Big Bang is a terminology which we might want to upset ourselves and change as we move through the rest of the talk. So there are fluctuations. It actually, and this is the scale of our horizon, and this is a 2-dimensional representation of what is, of course, 3 dimensions. And it's got the ups and downs in sort of a random pattern. And it is supposed to morph in terms of the microwave background into something that will ultimately look like this. So the ups and downs here will map into ups and downs there. And we understand this very well. And then, as time goes forward, it morphs into something that looks like this. So this is a lot smaller than the patch I showed you, but it is what we call the cosmic web, which is what it evolves to. And it is just the action of gravity that does this. It pulls all of the waves that we saw, the structures that had all of these ups and downs, but about equal numbers of ups and downs. And what it did, it drew the ups all together, and the downs evacuated to make voids. And so you get this beautiful filamentary pattern that very much looks like a cobweb with a very artful spider. And then in some places there are very big conglomerations, which in this case would be clusters of galaxies and superclusters of galaxies. Here's a very, very old representation of what it looks like around us. We call it the cosmic web. So I'm going to very quickly go through this just to give you an idea of how all of the entropy, the information, occurred in the universe. So, but you probably can't see it, so I'm going to go one beyond. I'm going to stretch the scale. There are a lot of red bits here in the centers of clusters of galaxies showing you how all of this sort of information is being developed. And then as you go deeper, it just traces the cosmic web. I'm going to skip over that. And we're now going to move into the ultra-early moments of the universe and the speculations that we engage in here, but using the information we get from here to try and look back to this very early area. There's a huge amount of work in this subject. We started with this. This is a realization of the way it might look within our horizon. And there's a theory, we call it roulette inflation, but there are many, many, many versions. For every theorist has their own inflation model, roughly speaking. We like this one because it emphasizes something really interesting in the universe, which is that it's fundamentally statistical. Kip showed some oddball-looking thing, which is associated with extra dimensions towards the end of his talk. And instead, let's visualize it as a Swiss cheese with holes in it. And so we have a theory of this, and so I'm not going to try and describe the physics of this. It's not feasible. What we're going to do is to just envisage what happens in a roulette wheel as the ball goes around and around and around, and then ultimately it slots in towards the winning number. And so we're going to focus here. Actually, this is physics, but we're going to focus on when it drops down. It's like dropping down a hill. This is our roulette ball. It's like dropping down a hill, and what will happen is we'll see ultimately that it will oscillate down at the bottom of the hill. But the key features are that the roulette ball will move. This is the move of an early field configuration in the early universe. And as well, there is something that is unavoidable, which is that there is quantum interaction, quantum diffusion, that causes this to go back and forth with some kind of jitter. This tries to move down there, and it jitters here. And then down here, you go from a state in which you've got this high rolling thing, which is dominated by potential energy, into something which has a lot of kinetic energy that ultimately dissipates into heat. And I'm going to show a quick movie of that, showing how complexity arises from simplicity. You're supposed to see simplicity here, which is basically uniformity. As you see the ball rolling down this hill, look what happens. It rolls almost back to where it was, not quite, but look what's happening to this medium. It's all getting caught up in terms of very strong interactions which start to appear. And so you're going to find all sorts of structures forming. And this is not just a trivial thing. It basically says what we have is a highly uniform medium that will become highly complex just by a simple rolling down of a hill with quantum mechanics, etc. being included, giving some very complicated state. That's supposed to be the origin of all of the matter in the universe, that kind of transition. The details, of course, we don't know. But we could do detailed simulations with all sorts of possibilities there, and we do that. Okay, so now I am going to move us through a little bit of the completely airy-fairy, and then into something really concrete like the dark energy. So we are going to go from the size of our universe here, what it looks like, to something a little bit bigger. Not a little bit bigger, sorry, 100 times bigger. So this would be the patch of the universe that we can see. The microwave background would be coming in from there. And we can't see this. This is outside of it. We can simulate it, but we can't see it. The assumption, of course, is that the physics that operates in our little patch of the universe is the same as the physics that operates elsewhere. That may be wrong, but that's the assumption that's being made with this sort of calculation. So you can do these simulations of what happens in regions that we can never see. The speed of light limit is the limit that defines the size of the region that we can see, the size of the region in which information can have come to us from the far distant past. And then you can go one beyond, and this is the most exotic plot, and I think even the people that made the plot don't understand it, because it's called the multiverse. And you can see it's a multiverse because there are many things that have the word universe on it. And what you're supposed to visualize here is that these are sort of like balloons, and each one has a different volume, and that's the key character, that there are some regions that will have a really vast volume and some regions that won't have as big a volume. And then the pictures that I showed you about that region that was 100 times of our universe, they'd be in one of these little things that would be called, within one of these universes, but we couldn't tell which one. And then our entire horizon would be a small bit within that. And so you can see that that's a really exotic thing. And yet what you do is you take the laws of physics, as Pythagoras tells us, is all described by mathematics, and you can go from what we can see out to regions that we can't see. Here are a few famous people who have worked on this. I've worked on it as well. Okay, let's see. Let there be heat. We've already done let there be light, let there be heat. I think I showed you this, but the real way it occurs is that complex pattern that forms, but what you actually do is you just heat up. The Fermi labs should be CERN's primordial soup can, the soup being of quarks and other such things. And I don't think you can see this very well. It's a three-dimensional complex representation of what happens. Anyway, that's showing you how complexity comes out of simplicity. Okay. Oops. Now I'm going to go to a final issue, which is the fate of the universe. Which is all wrapped up into what actually happens to this dark energy or cosmological constant. And I'm going to give you a visualization of the evidence that we have right now that the dark energy is like Einstein's cosmological constant. So this is showing you a line. This is the expansion of the universe. This is now. This is when it was half as big, and this goes back further. Most of the information we have is here. This line says it would be a cosmological constant. This includes all of the data we have now, and the fact that everything is bundling around a cosmological constant is showing that that's a very good model. That's with all of the current data. So here's our Einstein being relatively happy, and maybe it will be a cosmological constant, in which case we will have Einstein with his tongue out. But as you heard, he repudiated it. And so it should be actually Lemaitre's cosmological constant. Now, we have a glorious future with this petabit plus 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 of data, 10 to the 15 bits coming our way, with all sorts of satellite experiments, ground-based experiments, etc. And this, if the cosmological constant is right, this allowed region will get compressed to something a lot tinier, and that's what we can look forward to over the next less than a decade, that kind of step. Okay, so now I will end on a slight philosophical note. So we talked about the it from bit. Now we've got a different thought of what a bit is. The bit is the little bit of the universe that we can see. The it is the megaverse or multi-universe thing that we had that visualization of. It has also got a lot of information content. We cannot capture the information content of everything, only a little bit of it. And then the final thing that I will leave you with is that this is the medium, and the message is this. He is the one that received the message. The message is obviously a complex message. And the meaning of the message may change, but the facts, the information that we've received and drawn out from the universe will remain. And so whatever one's ideas are, whatever the revolution coming will be, you will have to deal with the information that we have already drawn about cosmology. On that note, I will end.
Take some questions.
Sir, I have 3 questions regarding the black hole. First question is, if a black hole is rotating or non-rotating, how would it affect its entropy? And my second question is, if ever microscopic black holes come into existence, how will it relate quantum mechanics with general relativity?
Okay, so I tried to studiously avoid the entropy of black holes in my talk, and it's something which there is, Hawking says so, there is an entropy to black holes. It is something that is, in effect, disconnected from any of our ability to access it. So let me give an example. In the centers of big galaxies, there are massive black holes. I think the limit was just announced of much more than 10 to the 10 solar masses. And so it's sitting there, and it's got more entropy than the entire cluster by a very, very, very large margin. But you don't get that information coming out unless you wait 10 to the 120 years. So, in other words, it's inaccessible information, at least from the perspective of any sort of experiment you can really imagine doing. So I must say that I do not have a heartful understanding of the nature of this sort of entropy, and I'm sure I'm not the only one. I have views about it, but I think it's a great mystery. People have actually tried to understand the entropy of black holes as enunciated by Hawking, etc., in terms of the number of actual states that could have gone into making it, and that if you could do an arbitrarily fine class of experiment for arbitrarily long periods of time, getting all sorts of arbitrarily large correlations between the different things that went into making the whole, then you would actually be able to reconstruct all of that information. I think in practice that will never, ever happen, but in principle it can, and that's the reason that Lenny Susskind won a bet against, not Kip, it was against Stephen Hawking, who said, yes, it's true that you could in principle regain all of the information that went into a black hole. And so I'm not really answering your question, and the reason I'm not answering your question is because I do not have a very clear way of completely understanding how thermal entropy, or information content, as I was referring to it, is totally related to this gravitational thing. People are trying to come up with analogs. I mean, it really is a leading edge question in physics right now, trying to find how this system and this system can be related. But we actually don't really know. Papers are appearing as we speak.
One last question.
Good evening. On the time scale of a universe, you told that around 14 million years ago, Big Bang took place and the universe was started. After that, some years after, protons, neutrons, all the basic elementary particles formed. Is there any theory or is there any prediction at which point does this dark matter and the dark energy comes into existence in the universe?
Yes, my guess is that John will actually speak to that problem. The best bet for the dark matter is that it was in equilibrium, interacting very strongly with the other matter that was present up until the time, which is much below nanoseconds.
But as far as I studied,
then it was released.
It was, I think, anti-particles, antimatter was there. In first nanosecond or first
That's right.
second. It was an antimatter and the matter.
Yes.
In the tug of war between matter and antimatter, matter wins, and so the world is, universe is made up of matter.
Yes, so it develops a slight symmetry.
I'm asking about this.
And then all of the rest of the more strongly interacting things, the matter and the antimatter annihilate, and they go and put their entropy, as it were, into neutrinos and photons. So those are the ones that are carrying most of the information. But earlier than that, the idea, at least within, you call it the standard model of the dark matter, the dark matter is interacting and is released, and it is not interacting at that point with the antimatter that's been present.
Okay, I think
it's released earlier.
will now stop this discussion because we have to move on. Let's thank Rick again for a truly phenomenal. And I invite Professor